Okay, Assalamualaikum warahmatullahi wabarakatuh, and hi everyone, ladies and gentlemen. Once again, welcome to the 62. Yeah, this is the 62 Distinguished Lecture Series proudly brought to you by the Faculty of Engineering, University Technology Malaysia. Yeah. Okay. And yeah, by the way, proudly brought to you by the Faculty of Engineering, University Technology Malaysia, UTM. And I'm Jay Suman from the School of Biomedical Engineering and Health Sciences, UTM, and I will be the chair for this session. Now, as usual, before we proceed any further, please take a few seconds to support this event by donating a click at the like button and follow on our Facebook page. And also we also have a YouTube channel. Don't miss it out here. It's Engineering UTM. So just type that word Engineering UTM, follow with our channel, click the like button, follow on our Facebook and YouTube channel. And please also share and spread the news of this event. Hopefully more people can benefit from the series. So today, as stated in our poster, our distinguished speaker for today's lecture is Professor Brian Hoyle, all the way from UK. And he is a prominent scientist in the field of electronic sensors and instrumentation systems, which includes the field of tomography. That's the same field as mine. I'm working in the field of ultrasound and electrical capacitance tomography with Professor Ruzairi and the team from University of Technology Malaysia and the rest of Malaysia. So should you have any question for the speaker in this session, please feel free to post it at the comment section and our team will assist you during the Q&A session later. So, okay, I will now pass the session to our Dean, Faculty of Engineering, University Technology Malaysia, UTM, Professor Dr. Engineer Muhammad Rafiq bin Dato Abdul Qadir to deliver his welcoming speech and further introduce our speaker. Over to you, Prof.
Thank you, Jai Suman, for chairing the session. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 62nd UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Brian Hoyle from the University of Leeds, United Kingdom. A bit about our distinguished speaker today. Brian Hoyle is Professor in Electronic Sensors and Instrumentation Systems at the University of Leeds. His research interests have focused on sensing challenges in a wide range of applications. He led teams that created the first real-time ultrasonic industrial tomography systems and the world's first real-time electrical capacitance T tomography system, applied in demanding in multi-component flow measurement in 1992. Later, he demonstrated the first use of machine learning methods in IPT. More recently, his work has pioneered multi-sensor data fusion for spectro-tomography. He is currently president of the International Society for Industrial Process Tomography. He also has extensive experience in exploitation and product development, with contributions to the formation of ongoing successful companies in spatial modeling software, in tomographic measurement technology, in assistive technology for the blind, and in clinical diagnostic tools. So that is a brief biography of our distinguished speaker. Here now is Professor Brian Hoyle from the University of Leeds, United Kingdom, with his talk on sensors, seeing the invisible, flying blind, and Ultracane and Ultrabike for visually impaired people. Professor Brian Hoyle, over to you.
Well, thank you very much for that amazing introduction. It's a great pleasure to be with friends and colleagues in Malaysia once again, both at UTM and also perhaps in USM in Penang. It's one of my favorite places in the world to visit. I'm looking forward to coming again. So let me start my presentation, ladies and gentlemen. So my presentation, as you've heard, is about sensors, and our colleague has just read the title. So let me go on and think about a little overview. What I'd like to do with you this afternoon is to look at how sensors help us to do things. And we've got three little topics that I thought might be very interesting to contrast how we can use sensors together to see invisible things. And we're going to look at tomography here, to fly blind, which is an interesting concept, and to help blind people to see, and perhaps also ride bikes. Interesting. So the overarching themes are, what does it mean to see? And also a little bit, perhaps, your colleague mentioned enterprise and forming companies, etc. And I've had quite a bit of experience, so I'm going to tell you a little bit about that along the way. So let's move on to think about this word sensors, and also the similar word sensors. Well, we take sensors to mean the things that you and I have with our bodies, for sight, for hearing, for touch, for taste and smell, the 5 things that we can think of that we have. And we can think of the sensors that provide those sensors. We have our eyes to help us to see. We have ears and fingers and mouth. But of course, the thing that really makes this come alive for us as human beings, quite literally, is the process that we have in our head, our very sophisticated computing tool, the human brain. And that's the main issue that I'd like to bring alive today a little bit, the idea of having multiple sensors and bringing together that information. So let's talk then about sensors. Without the ability to sense things, we can't monitor, control, or even make things. So sensors are a vital but almost invisible part of our society. So let's bring them to life. Let's think about this idea of seeing the invisible. We've got lots of experts, I think, perhaps listening in the tomography work at UTM. So let's just do a little revision here. Electrical conductivity sensing. Here, if I put a current in there into this little process, a cross section, I've got electrodes. The current will come out at the other electrode, and I can measure the potential difference around this process and work out perhaps what these equipotential lines are, and use that information with some inverse processing to work out what must have been in that space to deliver that set of measurements all around that process. We call that one projection. So we've got this rather beautiful image here, and this is a fairly vague image because you've only got a few little points. And I think when we talk about industrial tomography, we always have the problem of time. With human beings, we can sit human beings under an X-ray machine and say, lie still for a few minutes while I take thousands of projections of your body and create a tomogram. In this case, we only have time for a few short things, and we're looking inside a steel pressure vessel typically. So there's a little look at seeing the invisible. And this is a combination, of course, of sensors, electronics, maths, computing, and chemical engineering. So it's inherently multidisciplinary too. Well, if we think about a more realistic looking process, this is the sort of thing that we find in factories. This is an industrial mixer, rather like a large version of what you may have in your kitchen. There's a large motor there driving an impeller. There's lots of sensors here, pressure sensor here, and here's a little viewing port. So if you could see through the material, you may be able to see what's happening. But most materials are opaque, and that window isn't going to be very useful. So let's think about looking inside, and here we can look inside this and see that if we attach some here temporary electrodes, and we can then create beautiful pictures like this one, courtesy of my colleague Mi Wong at Leeds. And here we can see a little bit of color segmentation here, 2 or 3 different materials. You can see the impeller vortex being created here from this particular process. So we can really look inside this invisible process, which is normally hidden from us for safety, pressure, health reasons. This material may be poisonous, etc. So we want to look inside that. And so there we've got a beautiful image of inside the vessel. So we've been able to look inside. Now, we have this very nice word, distinguished lecture series. It's a great honor to be part of your distinguished lecture series. But in a sense, it probably means that you've been around for a little while, and my work in tomography started quite a long time ago in the 1980s, perhaps before some people in the audience were born even. So I thought I'd show you one of the first things that we did, and our chairman kindly commented about this. This is, I think, the world's first real-time ECT system. We did this work in conjunction with a company called Schlumberger, who are an oilfield services company based all around the world, and they have a large research laboratory in Cambridge in the UK. And in 1990, we used this flow loop, which is a 50-meter loop, which is inclinable from the vertical to the horizontal. So the vertical down to the horizontal. As you can see, it's slightly inclined here. And here's the sensor. You perhaps recognize it. It's got some electrostatic shielding, and I think it's a 12 electrode system, this. So this is 1990 tomography. Then we had very little computing power. This used a parallel processing system with about 24 processors to work on this particular computing exercise. So I'm going to show you a little video of this process running.
The pipeline in the Schlumberger laboratory in Cambridge has an
I'm
oil and
sorry
gas
about the quality of
mixture
this
just
video.
like the flow from an oil well. The difference in the dielectric properties between the two components allows us to visualize the distribution of the oil and gas phases using a method based on capacitance tomography. This is achieved by placing a number of electrodes, typically 12 or 16.
Got a slight little processing delay between what's happening in the pipe and what's happening on the screen.
The pipeline could be made of steel and on the seabed.
And here we can see the 66 measurements.
Readings used to reconstruct the image. In this example, we see that the gas rate will be decreased. The presence of gas can be seen occupying the top part of the cross-sectional image on the computer.
Well, that's a little look back in history. Let me just pause this. That's a little look back in history. And I think we then did about 100 frames per second on that particular process. And shortly afterwards, a few years after that, we founded a company based upon that work and also some work on ERT. And we started that company, and it's still very much developing. And I think it's probably now the world's leading company supplier of industrial tomography systems. Here we can see, for example, a large client base in measuring the density profile of a dredging process here, and I think there are now about 100 ships around the world with RTS sensors here, which replace gamma-based sensors, which are radioactive and cause lots of safety hazards. So that's a little look, a bit of enterprise forming information about how we look inside processors. I'd like to introduce you, if you haven't come across the International Society. I'm presently its president, which is a great honor to be, and we founded this particular international society based upon the virtual center that I formed with colleagues in Manchester from about 1999. I did promise you that this went back in time, and we inaugurated this international society in 2010. It presently has about 700 members, and interestingly, it's completely free to join. So if you want to join, you're very welcome. Simply register, and you can attend our next World Congress and present your research work and join the world's largest IPT event. There are some nice case studies on the website to look at as well, and lots of news and all the previous collections of World Congress proceedings which are available. And all the papers are available free access for members. So here's our next World Congress, a little advert here for you, ladies and gentlemen. And it's going to be in Tianjin next September. It was supposed to be in 2020, but for obvious reasons, it's been postponed by 1 year. So I look forward to seeing you at the ISIPT World Congress in a year's time. So we've seen the invisible, folks. So let's move on to our second sensing challenge, which I thought was quite interesting because it's one that we perhaps don't really think of. And that is what machines and animals are able to fly without sight. Thinking of moving around without sight as a sighted person is always rather frightening for me, perhaps for you too. So, can you perhaps think of what typical machines are flying around without any sight whatsoever these days, without any visual sensors? And animals that can do this too. Well, you may have come up with answers. I can't hear them. If you have, I'm going to sort of perhaps think that you might have said drones, perhaps. We know that drones have got video cameras. But the cameras on drones usually look around at the ground. They're not really used as part of the navigation system. And one little animal you might have thought of, they're all around the world, is the bat. And the bat has evolved using ultrasound. I know there's lots of interest in ultrasound at UTM. So the bats use ultrasound they create ultrasound with their mouth, and they've got very highly adapted ears to listen to the echoes, and they use the echoes in a special part of the brain that's evolved to process this stuff. Remember, we need to process lots of information to make intelligence information from that. So we know that bats can fly blind. Now the machine I'm suggesting can fly blind is an airliner. So let's have a look at an airliner. So here's a typical large airliner flying around today. It's a BA one, but I know that there are Malaysian Airlines equivalents of this aircraft. So it's an Airbus A380. The all-up weight of this aircraft is 500 metric tons approximately. That's 500,000 kilograms fully loaded, and it's carrying about 100 tons of fuel. So this is a serious machine, but there are no visual sensors to help it to fly. So let's take a look a little typical problem that we might have. If I want to start in perhaps London, where that aircraft is based, and fly to Los Angeles on the western seaboard of the USA, I'm going to have to fly west 118 degrees and south 17 degrees. Now we're looking here at this Mercator projection. If you've not thought about this too, which is a common way of looking at the world, and this is formed by imagining the Earth is a sphere, of course, which it is, and imagining a light bulb inside that sphere, and imagining that the surface of the Earth is translucent and we can see the shapes of the countries. If we then wrap a cylinder around that, where the equator here touches that sphere, then we get this sort of map. And it's fairly accurate near where the equator touches, but as we get further and further higher in latitude, south and north, we get a very large distortion. So this map isn't really a good way to look at long distance flying at all. It looks as though the best way to get from there to there is to take a route southwest approximately to get to, we'll be in LA very quickly. We just join that line, Pythagoras hypotenuse there. But in fact, if we take a little look at the planet, we find if this is the North Pole and here is London and here down here is LA at the bottom end of the USA, then the real best route is one that actually transits on a great circle across the planet. And let's think about this rather carefully. Now that great circle is a line that joins together 2 points such that if I carry on making that circle, the center of that circle will be the center of the Earth. And that's a great circle routing. And here, if I look now very carefully, instead of flying southwest, I need to fly northwest. And I need to then start progressively flying west. And eventually, I need to start flying southwest. And this is rather strange. I'm flying continuously changing headings here. If we take this distance, this is about 4,400 nautical miles, the ground speed about 450 knots, 520 miles per hour, about 10 hours flight time. So what's the heading to steer? Well, there isn't one really. We have to continually change our heading. So imagine doing this. If you ever thought about flying an aeroplane, it's rather like steering a car. You're driving this car for 10 hours and you're slowly, carefully, every fraction of a second, just turning the steering wheel just a little bit to the left. Well, we have a special office to do this processing. Here it is for the A380. It looks an incredibly complicated system, but in fact, this aircraft is designed to be really easy to fly. Here is the processing bit. So this is where all the information is brought together and we do navigation computation. Here is the engine management system. Here you can see the 4 loops here representing the engine instruments. Here is the primary flight display. This is about flying the aeroplane. And this is the navigation display. Here we would have similar things, but the aircraft's on the ground and these screens are being used to monitor the loading process here. So these 2 screens provide all the information that the pilot needs. And this flight control section here has got connections to the flight management computer which can take routings. It has all the world's routings in it typically, so it can quickly find a route from anywhere to anywhere else, register that routing, and effectively, shortly after takeoff, we have the pilot using the throttles here to power the airplane off the ground. As soon as it's clear that there are no serious issues, then the flight management system is executed and off we go. And this airplane is quite capable to fly that whole routing, including the microscopic changes in steering, until it gets and lands on the runway at LA. So this is a marvelous bit of integration. We've got thousands of sensors. Let's take a little overview. So to sense the position of the aircraft, we have some integral sensors. We have some inertial data sensors, air data sensors, magnetic sensors. We have some ground-based navigation beacons. These are microwave aids, and microwaves is one of the specialisms of my university at Leeds. And we have some satellite sensors as well, or we're sensing satellite data. And we're going to put all that together and get a continuous estimation of the four-dimensional position in latitude, longitude, height, and time. So that's what we're going to end up with if we take a little look at what's going on. So this is all the stuff on board the aircraft, and that means it can fly independently to a high degree without any external information. But we have the navigation beacons typically, and these give us distance from the aircraft to the navigation aids. They give us other information, but distance is the most valuable, precise stuff, and we can use these two crosscuts to locate our position continuously. And as the aircraft moves, it's continuously tuning different navigation beacons. And we have this marvelous satellite system. GPS or Navstar is one of them. The GLONASS is one operated by the Russian Federation. And we have other ones coming along as well now. And what we have here, in effect, although people on the ground might think that this is telling me where I am, all that satellites are doing is providing a timing information. So this satellite broadcasts a message saying, this message started at time T. And when I receive it here, I've got another clock on my aircraft. It's at time T plus a tiny amount. So I can work out that distance, and I know the position of that satellite because it told me in the message. So with all of these integrated measurements, which don't quite come together typically for all sorts of technical reasons, I have to combine them together. I can find out where I am, and I can comply with my need for what's called required navigation performance. Well, let's take a little look. We're here looking at flight radar, one of the systems that integrate information being broadcast from aircraft, and this is called automatic dependence surveillance. So all these little cartoons are real aircraft, and they're being monitored by radio signals that they're continually transmitting back, and that are collected and can be displayed like this. So we can see that this flight, it is an A380 BA269 from LHR to LAX, started at 4:18 p.m. It's due to land at 6:46, and it's just reached its cruising altitude, 36,000 feet. It's not climbing or descending, and there it is, not far from the city of Leeds, which is just here. So ADS-B is part of the future of ATC. It means that airplanes are like little navigation systems, and they tell everybody else where they are. And so we can always have a safe path. Of course, they do register flight plans, but we don't need radar surveillance. So if we think about the other end of this flight, here is the airplane now coming from the southwest. Well, it would be actually turning on this special routing to approach the airport here at LAX. And it's got to do, and it's descending as well. So this aircraft is currently on a track of 263 degrees, almost westerly, and it's doing 182 knots. So previously it was doing 479 knots, about 550 miles an hour. So here it's approaching the final runway. So I'm going to just show you a sort of technical map, which is called a standard terminal arrival, a STAR. And this indicates all various points of interest. It includes, one called SADE at this little point here. And that's a key point in this routing. which is coming here. We've got the southwesterly bit at the end. It's going to turn now slightly to the east, and then make a turn to the east, and then a turn actually to the east, and then start turning right to approach one of the 4 runways at LAX. Interesting things here. Required navigation performance. Typically here, the airplane is expected to be within 500 meters of where it's supposed to be, and the typical height requirement is between 16 and 8 meters. So this airplane has to keep within these particular this corridor in the sky. So let's take a little look then. This is its final destination, runway 24 right hand side. It's one of 2 runways on the right hand side of the airfield here, and we're just about to approach that. So as I said a few minutes ago, it is possible for this airplane to fly completely from London Heathrow, fully automatically fly this routing and land until about here, when the pilot would actually turn off the flight management autopilot system and start taxiing the aircraft and coming back to one of the stands here at LAX. When it's at this point, the required navigation performance is 6 meters horizontally and 2 meters vertically. So this is the requirements of accuracy and precision that are required at that point in the flight. And so this runway is 150 meters wide, and so we have to be within 6 meters of that. And we'll just see in a moment how good this airplane is at doing this little job. Well, this is quite an interesting thing. We've flown this aircraft now for 10 hours. It's done 4,400 nautical miles, and it's been within these parameters all the time of its flight, and that's thanks to the sensors that are on board the aircraft. So I'm going to show you a little video, and this little video is got a very loud pop tube, which I'm going to turn down in a second. We'll just turn it down a little bit. So we're now approaching the coast here through this little settlement of Thousand Oaks. There's the Los Angeles over here. Here is Malibu, the famous surfing beach, and Sade is a point, an arbitrary point somewhere. We're just coming up to Sade now. We're going to make that left turn, and the aircraft is doing this fully automatically. It knows this routing, and it's now following the Pacific Coast Highway 1 here along the Californian coast as we travel south now. And here is Santa Monica, very famous Santa Monica pier here coming up. So we're going to make a left turn now and approach the downtown area. Again, imagine this now without any visibility, quite common in LA. So we're approaching the downtown area. Here is the Santa Monica freeway, the motorway. So we're going to start making this complex set of right turns pretty soon as we go overhead the downtown area now. You can just see the at the front here, the dynamic pressure sensor, the airspeed sensor on this aircraft, or one of them. So we're making that first bit of a right turn now, going over the LA River, and we're now approaching, we're turning towards the south now, and now we start to turn west again, and we're now making the last of these major turns. So we're about 20 miles to run now. The airfield is somewhere here, and with this speed of this film is speeded up, of course. We're now doing about less than 200 knots, and the airplane is now descending in its required navigation performance to hit that runway, hopefully not too hard, as we make our final approach to runway 24 right. All these sensors are now working to deliver that 2 meters vertical height requirement precision at this point. And here we come in now to runway 24 right. This is our aiming point here. No visual sensors. We can see out the cockpit. The airplane's got no visual sensors for this at all. So there we go. So the pilot's going to take over about now. So we've done that 10-hour flight completely based on our collection of sensors and processing equipment on board the aircraft. Well, we'll just let this aircraft get to its stand. It's now doing the taxiing. This is one of the most difficult and dangerous bits of flying, being on the ground with other sharp things around. And at the moment, there are plans to try to automate this process, but nobody's finally agreed how this could be done yet. So here we go. We're just about to make our final approach to this stand, I think. And we're going to turn here. And here we can see the iconic sort of spaceship structure at LAX. And here we are, our final stand. So we made it. And we made it really thanks to a collection of sensors and processors on board this A380 aircraft. Similar to all the other sensors we have around. Sorry, I'm starting that one again. So let's move on to our next little challenge of sensors and how we can do something with them. So we've seen the invisible. We've shown that we can fly blind almost literally around the planet with very large machines. What technology then do we have to help blind and visually impaired people with their mobility? A colleague of mine asked me this question, and she is a neurophysiologist. I'll give you her name a little bit later. But she said, you guys can help us have phone calls with other people on the other side of the planet in video. And we've done lots of microwave technology to do this around the world. We've now got these very sophisticated systems. I'm using one now to be with you in Malaysia. And she said, the only thing we have for blind people are sticks and dogs. And if you look around, this is almost true. What we give to a blind person to help him or her walk around is a stick. It might be a high technology carbon fiber stick, but the only way they know that something is there is when they touch it with the stick. Or we can give them a seeing eye dog, as it's called in some places, or a sight dog, perhaps. And that dog, although it looks very nice to see these people with them, they can only work for a short time during the day. They cost a very large amount of money to train. And they do take away the independence of blind people. So you're not finding your way around. The dog knows where you want to go, usually. So it's not a fantastic solution. So we start to think about this. And when I asked you the question a few minutes ago, I suggested that you may have thought of the answer bats. And bats can certainly fly blind. And they've been doing this for millions of years. So bats hunt at night typically. Although they have eyes, they don't use light to see. We can find that bats can work in complete darkness. They don't need any light. And they verbalize ultrasound, pulse illumination, listen for echoes, process that to synthesize a view of the dark world. Here we see this bat just about to have its dinner. So let's move on then to think about this idea of sound and ultrasound. I know that there's colleagues at UTM who are doing lots of work on ultrasound. So I don't need to make this introduction for them, but let me make it for anybody else. Our human hearing is from a range of about 50 hertz to about 15,000 hertz if you're a young person with small ear parts. Now, ultrasound is simply higher frequency sound. It's not different at all. It just is the higher frequency. So this means that our ears can't vibrate at this frequency. But what we can do, if you want to listen to ultrasound, is simply use a bit of electronics to slow down the frequency. And a little illustration then is, if this is the 50 kilohertz, say, that I definitely can't hear, I can simply record it and slow it down in time. And I can do that continuously. So I can hear it at a lower frequency. So I'm going to ask you to take a little look with me at a rather special little video. Here is my colleague, and he's a bat specialist. You remember this idea of multidisciplinary science that I was introducing a little while ago, and he was one of the people who inspired the bit of technology we're going to see soon. So here he's got a friend of his, a bat. This bat was taken from the wild because it was injured, and so couldn't survive in the wild, and so it lives at the University of Leeds in the Department of Biology, where I think it's very well cared for. And we're going to ask this bat, which is clinging on a little net to fly to another net that's actually on the other end of the corridor here. Now this looks like a pretty fairly well lit corridor. It's very grainy, and it's not well lit in optical terms, because if we were standing in it we wouldn't see anything, because we're looking at it in infrared here. So we have an infrared camera here looking at this, and we're also going to listen during this video to sound, and we're going to particularly listen to ultrasound, and we're going to listen to this bat, and it's going to be making sounds that I'd like you to listen to, and we're going to get a lot of noise, but we will hear the bat. I'd like you to look at the mouth of the bat as it's flying towards us. So let's take a little look at this video. Well, that was my colleague Dean Waters, and as we saw there, I've just moved it on because the video will start again if I'm not careful. We saw there this bat, and the sound that we were hearing was about 40 kilohertz or so, and we've slowed it down by 10 times, and so it was 4 kilohertz. So that's well within our hearing. So we're hearing this machine gunning noise as the bat irradiated the sound around it with pulses of ultrasound. So that bat is using that with its ears and its very sophisticated brain, which is adapted for this. So it's using sonar. And if we take a little look at sonar, sonar reflects the sound of all common materials, from loose cloth materials through to plastics to glass, etc. And we can think about this at low frequencies anyway, from 10 kilohertz to 200 kilohertz. And this is what we're going to be trying to use. If we contrast that with radar, that sounds like a possibility, but radar only typically reflects well from metal. So sonar is a really good choice for this. And I'm going to suggest that we use 40 kilohertz because it's well above, it's well into the ultrasonic area, and it will give us very good spectral things. We're going to look in a second at the resolution we get from this higher frequency sound. So there we are. We're going to look at some sound, and I'm going to ask you to do a tiny bit of math. So we're interested in this wave. It's going to be at 40 kilohertz. We want to know the period and the wavelength. And we're then going to make pulses where we collect together multiple waves, the waves per pulse. And we want a duration of about 1 millisecond. So our two specifications are 40 kilohertz and a 1 millisecond wide pulse. And then we can send about 10 of these per second. And you might remember what the bat was doing, a beep, 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 and that about 5 a second or 10 a second. So we're going to try to replicate the bat. So if I move on and show you the answers to these things, life is easy when we've got the answers already worked out, isn't it? So here we've got a period of 25 microseconds and a wavelength of about 8 to 8 millimeters. And if you put your thumb and finger together and make about 8 millimeters, you'll see that that's about the resolution we can expect. If we create a packet of sound and listen for reflections, we're going to get a reflection back with a resolution of less than a centimeter. Now, that's great for blind people. If you can tell them where something is to less than a centimeter, that's a fantastic specification. So we want a pulse duration of about a millisecond, so we can send lots of these per second. And so we're going to make about 40 of those waves. So imagine this compression waveform moving through the air at that rate. So we're going to create 10 pulses per second. The speed of sound in air is 340 meters per second. It does attenuate quite rapidly. So this wouldn't work for 500 meters. We'd have no sound left. But at this frequency, it's going to give us very good effective range for up to about 20 meters. Okay, let's move on then. Here is the invention. Here is the Ultracane, as we call it. And the idea here is to use a standard long cane. So down here is a standard cane, so the blind user's got the ultimate fallback. Hopefully not really, the ultimate form of information that if the stick hits something, then that will give the user that information. But we're going to also not use the sense of hearing, because we're going to find that blind people really want their sense of hearing. And so we're going to use this tactile feedback. So imagine you holding this with your thumb at the top of there. Your thumb is here and your fingers are underneath, handling the hand grip. And so when you're holding it where the cane is angled to about 45 degrees to the ground, this transducer here, it's an electrostatic ultrasonic transducer, will be pointing forward and downwards in front of you. And this one will be pointing upwards ahead of you. So that one is pointing forwards, that one is pointing up. So this one alerts people to danger above, which is really dangerous for blind people. If they're using a stick and there's a ladder across the street or something, or a truck wing mirror, they will bump into that because they don't find it with a stick. So that's how the Ultracane works in principle. Let me tell you a little bit more about the tactor buttons. The forward button will vibrate there. That will show us that there's something ahead, and the upper button will vibrate that one. And so this leaves the sense of hearing free, and the blind person can use that separately, we're going to find, from their sense of touch. So these tactors, as we call them, provide the tactile warning signals, giving direction and distance of hazard. Direction in the sense that one is that way and one is that way. Now you might think, well, how do I work these things out? But let's remember, your fingers have got one of the most densely populated nerve surfaces on your body. You can easily detect something at one point in your thumb and at another point in your thumb. Okay, well, let's talk about brains. And I'll introduce my neurophysiologist colleague, Deborah Withington, who first told me about how hard it is for blind people to get around and how little we support them with our technology. So let's think about the spatial tactile cognitive mapping, how the brain works with this. Now, we did think about our 5 senses when we started. I'm going to introduce another sense to you, and this is called proprioception. And I'd like you to think about carrying a little experiment out. I'm going to do it as well. I'd like you to take your finger and touch your nose. And of course, when you've got your eyes open, this is easy to do because you can see your finger. However, I'd like you to close your eyes and try and do it again. And it's just as easy. You can touch your finger, you can touch your nose with your finger just as easily with your eyes closed. So it's not your eyes or your vision that are helping you to do this. It's the sense of proprioception that effectively is part of your brain, has got a continual monitoring system of all the important bits of your body that can move. So it works for your feet, it knows the position of your feet, and it knows the position of your hand. So it can detect the orientation of your limbs and feed that into your brain. And that's really interesting, because if we can form a human bat by adding some capability to our human being using the tactile data, we can give them that information so that your super effective computing brain can use that to work out what these tactile signals mean. So we're not painting a picture for the human being, we're letting the brain paint the picture, like your eyes that provide a picture in your brain using sight. So there we go. This is added context to the tactile data, and this is a learned adaptation. So we have to learn how to use this. And babies, as they're growing in the world, learn how to realize and learn that how to move their fingers and pick things up and learn. And if you think about the fantastic achievements that we have, imagine a concert pianist. It takes about 10 years, I'm told, to be a concert pianist. But if you're a concert pianist, you can use the very fine fingertips. You don't need to look at the keys. You can just read the music or take the music from your mind and play these super subtle movements with your fingers without looking at them and without thinking. All you think about is the music. So the Ultracane does that. And people say after about 1 month, they don't feel the tactile signals anymore. They just know that things are there. So the other bit of the brain we're going to utilize, thanks to my colleague Deborah, is this part called the superior colliculus. And this is in the lower brainstem. And this is an untrained awareness. We have this awareness when we're born. So if you try very gently, of course, just giving a baby a little nudge, it will turn its head to look at where that nudge is coming from. It's part of our fight and flee, I should say, a defense mechanism. So even babies have this capability. So the idea is, every time I hit your thumb with a little pulse, your brain wakes up and says, oh, there's a pulse there. What do I do with that pulse? And it will then take that information to the somatosensory cortex and add that to your capabilities. So we're literally effectively adding a new sensing capability to a human being to create our human bat. Well, let's take a little systems view of that. Here we can see the picture. We're taking a tactile stimulus, the two links in the brain, add the orientation position of the cane, and that makes a spatial map. And if we've got a prior memory of a particular journey, all that information is integrated, just as it was in the Flying Blind A380, and we can help blind people to see with ultrasound. So
navigating in the dark,
here's somebody doing this.
Cane uses ultrasonic signals which bounce off objects and feed back information via vibrating buttons, giving the user a much more detailed warning about obstacles than has been possible with the ordinary white cane. Well, Bill Gulliver, who you're seeing here in these pictures, used one of the canes this morning. And
so that's a news broadcast, just as a website here. That's a news broadcast that was when we first released this, and it's still quite interesting. And the gentleman there, Bill Gulliver, had that little device for about 1 day. So he'd not yet reached the stage, I think, of using it subliminally. And as you saw, he was simply pointing at objects. And when he found them, he just simply walked out of their way. So he was using the Ultracane, and as you saw, he didn't actually touch anything with his cane. Well, we formed a company again, a bit of enterprise, for this in about 2008, and this is the website for the company. It's very much about this as a product, of course. And there are lots of people around the planet now in lots of major countries using this, the USA, the UK, Europe. I'm not sure about Malaysia, China, Australasia, etc., using the Ultracane. And it's been very rewarding for me to hear people say that the Ultracane has changed their life by giving them much more confident mobility. Well, let's take a little look at some feedback from the thousands of human bats that we have. Without using it, when using the Ultracane, people think I'm faking being blind because I tell them where things are, and so. So we get people saying very nice things about this. Here are a couple of human bats. You'll notice these two guys are identical, and tragically, they are identical twins, and tragically, they both lost their sight within a short time of each other because of an inherited condition they didn't know about. And one of them is a keen cyclist, and we're going to meet him again in a few minutes' time. So both have become human bats, and this is another not blind person who I'd like to introduce you. If you're interested in motor cars, you may have met in the TV Richard Hammond here, who was very famous for the Top Gear show, and now something else, I think the Grand Journey or something he's doing. And here Richard, as part of a BBC broadcast, was interested in this because he was having a TV series on biomimetics, the sort of science of technology imitating nature. And this was going to be called Miracles of Nature. And as you can see, here is Richard and I, we're just talking about this as he starts to do some filming. And Richard asked if we could fit an Ultracane to a car. And we said, well, that's really difficult. It'd have to be very artificial. We did agree to a bike. So we built an ultra bike. And if we look at this view from overhead, here's the person, there's his head, there's the handlebars. You can see this idea, instead of looking forward and upwards, there's no obstacles above, we're looking left and right. And we've now got the ultrasonic beams going to about 8 meters or 26 feet. And so as this person starts to feel the sensation, he or she will feel the fact that they're approaching this obstacle and start to stay a few minutes in the program, a little extract from the program, which is interesting, by Richard Hammond, and here's the various parts of it he did. So we're going to see one of those now.
I want you to watch the next 30 seconds very carefully. In just a few minutes, a second rider is going to come down this track, through the same twists and turns, over the same humps and bumps, but with one big difference. This rider is blind. So how is that possible, when practically all he sees around him is black? This man, Professor Brian Hoyle, believes he's found a way to do just that, by putting bat tech in a stick.
So this isn't just a bit like the way a bat works. This is echolocated.
It's very, very similar indeed.
Okay.
Over to you.
Right. So it's beeping at me. That was you.
It was me.
It's found
yes,
you.
Felt me.
Look at
yes,
that. And if I
here.
move it off, it stops.
I'm going to go behind you so I can see what's going on.
I felt you walk through. So what I'm doing now is this is sending out a noise, the same as a bat does, and then listening for it bouncing back, echoing back off objects, which is exactly what our bats did. It then tells me by buzzing
Absolutely.
on this, and you can feel it in my
Absolutely.
thumb. So if I walk towards that, it's found something.
Just take it slowly.
It's buzzing through my thumb.
Ah,
But
good.
if I move off,
Yep.
it's not.
Great.
So it's telling me there's an object
So
to
you
my
found
left.
a safe path to the right.
And there's nothing to my right. Nothing. Nothing. Oh, there's a sudden buzz at my. Now, if I move off to the right, nothing. To the left, something. To the right, nothing. So I would know I'm okay going this way. And it gets faster as you get closer to it. It buzzes through your thumb more quickly.
That's great. Absolutely.
Well, you don't need me to tell you, Brian, that your invention works, because it does.
Fantastic. Great.
Bring on the blindfold. Let's give this a proper go.
Right, let's see if I can pick up in a matter of minutes what it's taken the fruit bat millions of years to perfect.
Nothing. Oh, something to my right. Hang on, there's a gap there. I've got something to my left there and to my right there. Picked up something then. Oh, that's a mannequin, isn't it? Slowly but surely, I can see how somebody could build up a picture. Right, only thing is, I've no idea where I've ended up. Right, I had no idea that I was here.
Well, I think you did really well, and I don't think you bumped into anything.
I didn't hit anything.
Surprisingly, that's not down to luck, but to my brain.
And what you're doing then is this information goes into your brain,
Yes.
and it's processed through the same part of your brain that actually processes sight.
It is.
Which means when we talk about using this to see, as far as your brain's concerned, you really are. You're building up the picture in the
I
same
think
place. You're seeing.
If we think it's the brain that sees, not the eyes,
Yeah.
then you're seeing.
Right.
Yep.
And that's the remarkable thing. Our brains can adjust astoundingly quickly to using our senses in a completely different way.
So I thought, what if we take this whole idea a step further and use bat sonar to enable blind people to do something they wouldn't normally even attempt? So I've taken apart a couple of canes and I've come up with this, the bat bike. Now, let me
talk you through this. Essentially, it was a prototype at the moment, but it shows the principles. We've got 2 back-cane handles up here on the bars with the contact pads feeding back information to the rider from the sensors in the handles themselves. And we've got 2 more down here. I reckon that should be enough information feeding back to the rider to enable a blind person to ride a mountain bike down a mountain bike course. Now, I'll say it out loud. Yeah, that is quite a big ask, but it could work. By the time engineers have built our bat bike properly, a few of the details have changed, but the theory remains the same. These sensors send out and receive a series of clicks, and a couple of vibrating buttons tell the rider what's up ahead. But now it's actually come to it, I'm not sure who's more nervous, me or 21-year-old Dan Smith, who actually has to ride this thing. A keen cyclist, Dan tragically lost his sight 9 months ago from a rare genetic condition. He hasn't been able to ride a bike on his own since. Although most of the damage to his eyes is invisible, trust me, Dan can't see anything in front of him.
5, 4, 3, 2, 1, go.
Dan only had a few short hours to practice on this bike. But that technology is allowing his brain to see the course. Well, there can be no clearer proof that bat tech works.
Yeah, very good actually. So very good to be back on a single bike again. But the technology works because I've just navigated the whole track by myself. So I'm very pleased, yeah.
Now, obviously, it might be a little while before visually impaired cyclists take to our roads, but bat technology may just have opened up their lives like never before.
Well, hope you enjoyed that. It's always interesting to see TV programs being made and a little bit of invention. Obviously, I'm afraid that Richard didn't invent the ultra bike, and we formed it from the previous things that we had. Well, we thought that that was the end of our ultra bike career and that we would concentrate on making the aid. But this was in 2012 when we did that broadcast. But shortly afterwards, we had lots and lots of interest. Lots of blind people wanted to try out our ultra bike. And so we designed a rather more robust engineering version where, as you can see here, the sensors are actually embedded at a particular fixed relative angle, a small one. And this is made as a kit that can be fastened onto bikes. So in a little bit later that year, we had what we think would be the world's first ultra bike event in the city of Bristol, where we did some of that filming. And various blind riders tried the ultra bike on a marked track. So this is part of that little preparation. And here is the young man who rode the bike, Dan Smith, and we're on this open area, and we're going to be using these crowd barriers. And if we, I think the ultrasound experts will realize that the scattering cross section to ultrasound of these simple little metal bars is very high. So we get lots of scattering back, and this is it's just like having a wall there, and it's easily detectable by the Ultracane, the Ultrabike. So let's take a little look. Here is Dan Smith on that track. We're seeing some pictures of riding around. We created this track, and so we had again. So we had lots of, we had about 40 people ride bikes, all of whom were blind. And we now have, my original concept for the Ultrabike was to have a three-wheeler bike, but the idea of not balancing was not anything like dangerous or adventurous enough for the TV program, but that was my original concept. So here we have people who are willing to have a go on a bike, and they're blind. So the balancing does take a little while, and now we also have products that are typically used on three-wheeler bikes. And we're still, and the company, Ultracane company, is still making these kits, and it doesn't sell them to the public. And obviously the last thing that you can use is an Ultrabike on the public roads, but they are used by colleges and institutions for blind people where there's a safe track, etc., for people to try. So that was a very rewarding experience. We also had an exhibit of that at London Science Museum. You can see here the Ultrabike kit and a few bits, and a picture of the guy Dan Smith there as well. So that's been very rewarding. So in terms of integrated sensors then, I hope that I've shown you how putting sensors together, particularly with powerful processing capabilities, does let us see the invisible, does let us fly blind around the planet, and does let us help blind people with mobility. So thank you for listening. I understand we're now going to have some questions. If you are interested in tomography, or you are interested in the Ultracane, there's a couple of things there. I just have to acknowledge the courtesy of Oxford Scientific Films, who made that particular film, and their permission to show it to you. So I think we're now going to go back, I think, to the presentation. So I think I just need to close this and to stop sharing my screen, perhaps.
Yes, Prof. Yeah, that was an amazing presentation.
Thank you.
Ladies and gentlemen, yeah, I think it's time for us to maybe just proceed with a short Q&A session. I hope you're still on board with us, and please buckle up your seatbelt. And we are going for just maybe one question, because due to time constraint. And by the way, Prof, Ultracane, that invention is something different than what we have seen in the market. That's amazing, Prof.
Thank you.
So
there were lots of other people involved in all of these things, I should say. Several other people involved. In publications, you can see other people's names there as well. I mentioned a couple.
That's truly inspiring.
Okay.
All right. So should we just take one question from the floor? I mean, from the comment section, if you have any. From the technical team, if you can assist us. Yeah, we have one from Hani Azmi. There you go, Prof.
So the question is, how has capacitance tomography evolved in terms of research industrial applications? Well, I think there's been lots of capacitance work around the planet. We have lots of resistance impedance work as well. But capacitance is very useful for oil flows, where we're looking very much at dielectric materials and not conductive ones. And we're looking now at very advanced systems, which can actually detect very tiny amounts of permittivity change. And typically also we're using capacitance tomography in association with other modes, such as ultrasound. And I think our colleagues in China are using dual mode ones, and the company ITS has a dual mode tomography instrument as well. So it's a very perceptive question. Thank you very much indeed. And I think if you take a look at the isipt.org website, you can look at all of the events that we've had, all the World Congresses, and we have several sections in those on capacitance tomography, and I hope you find lots of inspiration answers from those.
All right, then. Due to time constraint, I'm afraid we have to end the Q&A session for this session. So it's been an honor for me to share the virtual stage with you, Professor Brian Hoyle. So with this, I will call in our Dean, Professor Rafiq, to do the closing remark. And once again, thank you very much, Professor Brian Hoyle.
Thank you. It's been a great pleasure.
Thank you, Dr. Jaisuman, for moderating the session today. And thank you so very much to our distinguished speaker today, Professor Brian Hoyle. You know, you have shared with us lots of very amazing stuff there. And we had more than 150 viewers for this particular session. And we received very positive feedback, you know. They says that this is a very interesting application, you know, very impressive, that kind of stuff. So congratulations to you and your team on developing these applications that so that our aeroplane can fly blind, and this Ultracane and ultra bike stuff for visually impaired people. So again, thank you so very much, our distinguished speaker today, for accepting our invitation to speak at our distinguished lecture series. And to all of our viewers worldwide, thank you for watching. Do stay tuned because we have many more lectures for you. Until then, bye-bye for now. Bye-bye.
Bye-bye. Thank you.